So I would like to convey to you the flavor of Euclid's Elements, the great masterpiece of classical Greek geometry. So the Euclid's Elements was the gold standard of mathematical reasoning and exactness for thousands of years, and it embodies the axiomatic deductive method, which more or less every mathematician ever since has aspired to the same ideal as Euclid. So for this, in these ways, it is an essential work certainly for comprehending all subsequent mathematical development. So Euclid's Elements then is based on the following principles that I have listed over here. The postulates in the right-hand column are the 5 postulates of Euclid, the 5 axioms, so to speak, which are the principles from which Euclid aspires to derive all geometry. So it's a very minimalistic program, you might say, only a very few assumptions. On the left column here, I have listed some of the definitions of Euclid, which we will also need, but from the basis of only these handful statements, I'm going to see how you can get very far and develop rather deep questions on the basis of only these few notions. And so Euclid obviously goes very much further than us, but it is, so we will try to understand the spirit of it. Look at this, the first 3 postulates over here are saying, basically, you might translate them as saying that you have a ruler and a compass, and that's why I have this little illustration here from a later title page of translation of Euclid, which contains, which then puts in visual form this paradigm that you do everything with ruler and compass. So you see that the first 2 postulates here are about that you can connect any 2 points with a straight line, and once you have a straight line segment, you can always extend it further and further just by, this is the kinds of things you can do with your ruler, obviously, or a straight edge, as it's called sometimes, because it does not have obviously metrical markings on it. It's just for drawing lines. And then the postulate 3 obviously gives you the ability to draw a circle, which is what the compass accomplishes. So that's those are the basic drawing tools of Euclid, and that's illustrated well in the very first proposition, the use of these, how Euclid relies on these construction principles. So here is a given line segment, and the goal now, the task, is to construct an equilateral triangle with all 3 sides being equal. So I already have this chunk that is provided for me here, and I now need to make a triangle which has 3 of these guys pieced together. Very well, I use postulate 3, which tells me that I can make a circle in this manner. So I use the given segment there as the radius of my circle, and one of the endpoints as the midpoint, obviously, and then the radius to make the circle. So, okay, fine, I just use postulate 3 to do that. Then I use postulate 3 again, obviously, to make another circle with this centered at the opposite endpoint. Very well, and now I can use postulate 1 then to draw a straight line from any point to any point. That's the postulate, so I can connect any 2 points. For instance, I can connect the endpoint of this segment that I started with to the new point that I created, which is the intersection of the 2 circles. So then I just place my ruler there and I connect. So nice. I do the same for those the two endpoints of the base segment, and now I have this triangle over there. Is it an equilateral triangle? Yes, it's an equilateral triangle because of what it means to be a circle. Just like the definition says there, basically that the circle is, all the radii of a circle are equal, so to speak. So that's how we know that these two, that any 2 of these are equal, so that the new segments that I constructed are the same as the base segment because they are both radii of the same circle. So that's how I constructed an equilateral triangle. So success. So you see how I kept referring back to these specific assumptions at every stage. Very typical. So that in that spirit we are supposed to build up all geometry. We're not supposed to make any hidden assumptions or anything. We can only use this list of assumptions that is available to us here from the axioms, and use all the rest we have to build up from there. And so that's the very first proposition in Euclid's Elements. Now let's consider another problem. I would like to make a parallel line to two parallel lines. Well, you might say, in fact, that the first proposition, Euclid's element, the equilateral triangle construction, is a very good starting point for making also parallel lines. I'm going to show you how you might reason in such a way. So namely as follows. First, I start with my equilateral triangle that I built from before. Now I can use postulate 2 here, which says that I can extend any line. So I extend the base, for example, like this to the right, why not? And then I use the same construction I already used before to make another equilateral triangle sitting next to the first one. Just repeating all those steps. And then I connect the top vertex of these two triangles there, the two top vertices, with again my ruler postulates. Obviously I can just connect and go across like that. Okay. Well, that's pretty neat. And then, you know, in the same way I could just keep fitting these equilateral triangles next to each other in this fashion, and now you would say, aha, I have made two parallel lines, haven't I? The bases of all these triangles and this line through all the vertices of all these triangles. And see, that's it's a constructed two parallel lines. So this, you might say, maybe Euclid put this as its second proposition, its elements. If it started with the equilateral triangle, this seems like a simple enough extension. You just repeat it a bunch of times, put equilateral triangles next to each other, one after the other, and then you have parallel lines. So that could be the second maybe thing that Euclid does, maybe. Well, I'm going to say, no, that's not the case, and I'm going to illustrate why, in fact, this won't do in an axiomatic, in the Euclidean. It's not up to Euclidean standards, this particular proof. So certainly you might say, well, look though, the heights of all these triangles are the same here, so surely the lines, they would have to be parallel, because you see that they have this fixed blue distance between them at all these various places. So how could they not be parallel? I mean, and just like the definition of parallel says over here, which I highlighted, so parallel straight lines are straight lines which do not intersect when they are extended, no matter how far they are extended. This is what Euclid's definition of parallel lines says. So yeah, I mean, how could they ever intersect these lines then? Because they always have a certain this blue length between them. No matter how far out you go, you always can have that gap between them, the blue thing. So that means they wouldn't intersect them. Isn't that what you would say? Well, not so easy. So first of all, we have one of the issue which I wrote down here, is that the is equidistant and the same thing as parallel. I mean, if I prove that they are equidistant, meaning the distance, the blue distance here is always the same all the time. So there's always the same distance between these two curves. But does that mean that they are parallel lines? Well, it's not what the definition says. I mean, if the definition said parallel lines are lines that always have the same length between them at every no matter which point you pick, well, then maybe you could say that this was the construction of parallels, but it's not the definition. Or we cannot make up everybody knows, oh, of course they're parallel, of course, because they're this. Well, we can't use this kind of course reasoning when we're doing Euclidean geometry. We have to use exactly what the axiom says, and that's a little bit different. So you might say, surely they can never intersect each other, these two lines, because of the equidistance property. Nevertheless, it's not immediately obvious from the definition as such. And for example, here are some issues that might arise. So really what we proved here is that they're equidistant at certain finite interval. These blue lines, they come one after a certain distance apart, so to speak. So how do we know we're not in the situation of this little picture that I drew down here on the right, that we have a scenario where, okay, they're so far apart here and they're so far apart here, like the blue line. However, they intersect in between maybe. Who are we to know? Based on this equilateral construction, the triangle thing that I made, we don't really know what goes on in between us. Well, of course, we can all see that obviously they're not going to intersect, but nevertheless, we are not allowed to rely on such common sense kind of intuitive notions, and we have to somehow derive this information from the axioms. So this leaves us in a bit of a bind. Maybe we could resolve this somehow, but nevertheless it's an issue, the fact that we have only proved this blue thing is the same at some points is not to say that it's the same everywhere. So, well, that puts us in one bit of a bind there. Here's another conundrum that might occur. Equidistant. I can just keep saying these lines are equidistant. Well, have I really established that in a sensible way? So I drew another illustration down here where I have two lines that do in fact intersect, and nevertheless I could fit as many of these blue line segments as I wish in between them by just tilting them. Well, then you might say, oh, no, that's not what I meant. I meant equidistant. In my example up here, really what I meant was that the equidistant line, the blue line, is perpendicular, you see, to both of the lines that I'm talking about, and you're not allowed to tilt it like that. But then you can so that's another one of those kind of pitfalls that you have to watch out. So it's not maybe so very obvious that what if you want to prove that two lines are equidistant, you have to prove that not only that you can fit a given line segment between them again and again and again, but you also have to prove that that line segment actually does represent the distance between them in some other sense than just the sense in which it is written down here in the right counter example kind of picture, because in a sense the distance between these two lines is the blue line segment, and I can repeat this process infinitely with these little blue guys. I can just tilt it a little and fit it in again, tilt it a little and fit, so that is a potential conundrum. So somehow we have to address that as well when we are going to prove that these are parallel lines. So a very complicated business to prove that we are not in this kind of scenario. Here another issue with this proof, again, its problems keep stacking up. It kind of goes on forever. I mean, the definition of parallelity, it says that in order for them to be parallel, it has to be that they never intersect, no matter how far you go. You can just keep on extending. So if I'm just doing this thing where I'm stacking up these equilateral triangles, you'd think I could just I can only go so far. I mean, I can put maybe 100 of them after each other, and then I can say, oh, look, they're not going to intersect because, look, I can always make these triangles. But somebody might object and say, well, you only proved it up to that point. What if I kept going further? Maybe then they intersect. And then you can just keep adding triangles and be like, well, but, aren't you convinced yet? Look how many, I can always just keep on going. But, well, somebody could always object that you haven't gone far enough yet. And so if you want to say that if you want to really complete the proof, you have to sort of assume that you have made all the equilateral triangles, so kind of all the way to infinity, so to speak, which is a questionable assumption because you cannot actually do infinitely many things. So now you're left in a bit of a dubious territory there when you are starting to talk about drawing infinitely many triangles, so which is not really something that can in fact be constructively carried out. So you see, all of these kinds of issues arise here. Here's another problem with this construction. So when I first drew the top line here through the vertices of the triangles, I drew it through the vertices of the first two triangles that I drew. It's the middle guy and the guy to the right of the middle. The two black dots. So I connected them with a line, but then later I just assumed that the vertices of these other triangles are also on that same line. Well, that's not really immediate, though. I would have to prove that, and it's not obvious as such from the axioms that also the red points are all on the same line. So who knows? And even the construction is even asymmetrical, because I started with the triangle in the middle, and then I spoke of the triangle to the right of him as the one that I used to construct the parallel lines. So would it be the same if I did it on the left? It's a little funny that we have an asymmetrical definition, and the concept of parallel lines has no concept of right and left or one side rather than the other type of asymmetry. So it's not so beautiful that the construction has this asymmetry in it that I go to the right. So all of these issues. So really this proof is a mess. And Euclid indeed does not put this as a second proposition of the elements, as I try to suggest that one might in a naive sense. So this is exactly the type of, to appreciate Euclid's elements, you have to consider these kinds of pitfalls that, you know, Euclidean reasoning, it looks clean and simple, but when you think about all the potential errors that one could fall into with this kind of reasoning, you see that Euclid really thought it through in great detail. Now, how do I really construct parallel lines, though, for real this time? Well, okay, I start again with my construction of equilateral triangle. Here's the same old story, but this time I connect also both the intersections of the two circles. So before I just use the top part there, but I can draw that, and then I have created a right angle here where it intersects the base of the triangle. It's a right angle because the definition of a right angle is that you split you split the neighborhood of a line into 4 equal pieces, so to speak, or 2 equal pieces on each side of the line. So you take the 180 degrees on one side of the line, so to split, and you cut it precisely in half. That's what a right angle means. So this construction is quite clearly completely symmetrical, so it doesn't favor one side rather than the other, and therefore it must be that it cuts the angle precisely in half, because there's no right or left tilted one way or the other or anything like that. So that therefore it's a right angle. So now I have a constructed right angle. I can forget about those construction lines that I drew. I can erase them later, and then I have here just the construction of one single perpendicular line, and then I can just repeat that same process with all the circles and all the blah 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 to make another perpendicular line, because what I just learned was that I can make a perpendicular line, and then I can apply the same method again. So now I have this scenario where I made a vertical line here perpendicular to the first horizontal, and then another horizontal perpendicular to that second line, vertical line. So, well, are these parallel then? That's the question. So if I look to the definition of parallel lines, they're supposed to never meet. Okay, I know that there's a 90-degree angle here and here. Does that mean that they never meet? Well, that's also not the definition. Nevertheless, I am proposing to prove it in the following way. Let's say they're not parallel. If they're not parallel, that means they do meet, they do intersect at a certain point. But then they must also intersect on the other side when extended in that direction, because of the symmetry of the right angle construction that we just talked about. If I have right angles on the right here, where the guy is going off to intersect, then I also have right angles pointing in the left direction. And because of the complete symmetry of this construction, there's no reason why the right side of the picture would behave one way and the left side in another way. So if it intersects over on the right, it also has to intersect on the left. But then I arrive at this contradiction, and because I have these two lines which intersect in one place and then they intersect again at another place. So that's a contradiction. You might say it contradicts postulate 1 here. Although, so Euclid's postulate 1 says to draw a straight line from any point to any point. That he says if you have 2 points, you can connect them with a line. But you might say it's implicit here. What Euclid means maybe is that there's precisely one line to the two given points, and that's kind of almost implied by the postulate. So there's only one line. If you have two points, determine one unique line, and you couldn't have two lines like in this scenario where I have the intersection on the right and intersection on the left, and there are two lines going to the same 2 points. So that wouldn't so that's a contradiction then if you interpret the postulate 1 in that way. So now I have proved the parallel that these lines are in fact parallel by reducing it back to the axioms that I had. So this is an example of then a more successful argument for construction of parallel lines than the first one that I studied before. So let's have a look at the fifth postulate, the so-called parallel postulate. That's the one that talks about parallel lines. However, it's not so useful for the construction that, we didn't make any use of it in our construction because it's very limited in it's minimalistically formulated, and it doesn't speak about parallel as such. It only speaks of, it lays down conditions for when lines are not parallel, rather than for, it doesn't saying nothing actually about the situation where they are in fact parallel. So the postulate itself is long and complicated, but here's what it means. It means I have two lines. I would like to check whether they're parallel or not. In order to do that, I draw a third line, this blue one, a kind of control line to check. I draw the control line and I add these two angles together, the interior angles on one of the sides of the control line there, and then I check it. Now what the postulate says is, if the sum of those two angles, that are alpha and beta, is less than two right angles, then the lines will cross on that side, in that direction. So if those two add up to less than 180, it crossovers over here. If they add up to more than 180, then it's quite easy to see that then they have to meet on the other side of the thing. So this leaves us then with the situation, what if they do add up to two right angles, 180 degrees, the alpha and beta, the two angles? Then what happens? The postulate doesn't say, it only talks about the situation where it's more, or actually less, but also more follows quite simply. But what about equal? So, well, there are two, there's like a two-way implication to consider here, whether in fact the situation where the two add up to when they add up to two right angles, is that equivalent to the lines being parallel? Well, we, in fact, at this point, we can already say that certainly if the lines are parallel, then the two angles will add up to two right angles. That's the I marked it with this green exclamation point because that part is safe, it's established, it's known at this point. Because what we proved before is that if it's not 180, they can't be parallel. So therefore, if they're parallel, they have to be 180 because all the other options are ruled out. So the only way they could ever be parallel if it's two right angles. So that's why the green one is in the clear, because we have ruled out all other options for the possibility of parallel lines. However, what we haven't proved is the arrow on the right, the arrow going upwards, that implication. So I marked that with a red question mark because it's not clear yet that when I draw my control line and it does add up to two right angles, then are they in fact parallel? We don't know for sure. The postulate doesn't say, and that remains a mystery for now. But nevertheless, using only this green part that we do know is powerful enough for many purposes. For instance, let's consider this proposition from Euclid, proposition 29 from book 1. I'm going to prove that these alternate angles here, the beta and the beta prime, the blue one, these two betas are in fact equal. So this is obviously a simple fact, but how can I prove it from using the axioms? Well, I apply the fifth postulate here in a way, because I have, by assumption, these two horizontal lines are parallel. Therefore, it must be the case that the alpha and the beta add up to two right angles. This is the part with the green exclamation point that we established before, because so that part, I'm just using that part that's already known. On the other hand, though, it is also clear that if you look at the alpha plus the blue beta here, then they also make two right angles because they are together the space on one side of a line. If you forget about the control line, you just see that it's like a 180 half turn type of setup, and therefore that's two right angles. Obviously, that's clear enough from the definition of what a right angle means. So yeah, and therefore putting these two equations together, I get the result that I wanted. I get that the blue beta equals to the black beta, so to speak. Beta prime equals beta. So those two are equal. So now I have established this result. Very nice. And for that, I only needed the green exclamation point part of the variant of the fifth postulate. So That's very beautiful. Now I would like to prove that the angle sum of a triangle is 180 degrees, as it's called, or two right angles, as we say in Euclid. So here I have some triangle, whichever triangle you can think of, and I choose to construct the parallel to the base through the top vertex there, like so. We already learned how to construct parallels as one of our tricks in our toolbox nowadays, so why not use that? And then this angle gamma, the blue one, is also the same as this angle up here is also gamma, because that's the result that I just proved on the previous, just a few slides ago. That's the result about the alternate angles. So that's nice. Those two are the same. And now, here's what I do. I use one of the sides of the triangles, which are marked blue here, as the control line, so to speak, of the parallel postulate. And then, if I apply that, I get the fact that alpha plus gamma together, they make a one of the two interior angles involved in the parallel postulate, and beta makes the other. So together, all three of them have to be two right angles, because this is again relying on the green exclamation point part of the parallel postulate corollary there that we described earlier. That if they are parallel, these angles made by the control line, they have to add up to two right angles, because if they didn't, they couldn't be parallel, which they are. So that's neat how we can get pretty far then to pretty profound results, like the angle sum of a triangle and so on. Very easy. These postulates are so well designed to achieve this kind of thing, and if you reason with in the right fashion, in a stringent way, you can reach pretty soon very striking results, starting only with these few assumptions. So that's the spirit that I'm trying to convey here with this. Here, the only postulate that we have not yet considered is the fourth one, and that is that all right angles equal one another. It says, what a funny postulate. Why would you even make that an axiom at all? All right angles, what, 90 degrees equals 90 degrees? Isn't that obvious? Isn't that, why would you even need to make an axiom out of that? Isn't Euclid, making a fool of himself, but just putting some obvious thing like that in a postulate? So no, he's not. Euclid knows exactly what he's doing, and as in so many times before, Euclid is a great master, more so than you might think at the first sight. Here's how to prove that the fourth postulate is indeed very profound. Consider a cone, like a traffic cone or an ice cream cone. That's what I have drawn here. And then construct a straight line that passes through the vertex of the cone, the apex of the cone. And that's what I did in blue here. So it comes up on one side of the cone, and then the dotted one, it's on the back of the cone, going back down again. And this, you can argue, is a straight line, because Euclid's definition of a straight line I highlighted here is a line which lies evenly with the points on itself. Well, okay, that's not really a very clear definition, honestly, but in any case, you can argue that this is a line because it's going kind of straight across the top of the cone, and there's no, it has equal amounts of space on either side, and it's just so certainly it would make sense to consider this a straight line, this blue one over here. One could argue that it's a straight line in the sense of Euclid. So that's a straight line, and then here's another straight line, the one that follows the wall of the cone the other way around, compared to the blue ones. The blue one is so it's just another line like the blue one, except oriented in a different way. It's rotated around the top of the cone. And now I say that in fact this creates 4 right angles, because if you look at the definition of the right angle, you see that what it means is that you have a straight line like a blue one being, and then you have another straight line coming in like the red one, which cuts the space in half, cuts the angles in half on either side of the blue. So but that's you can have that scenario with this red and this blue here, that I arranged it in such a way that the red comes in precisely midway through, so to speak. It doesn't. It's not closer to the solid blue part or to the dashed blue part, but it goes right in between, so to speak. So that makes it right angles in the sense of Euclid. However, these right angles are not 90-degree angles, so to speak, or they're not the same as right angles somewhere else, and that is because the cone point is has kind of less total is less than 360 degrees around, so to speak, at the vertex of a cone. That's what I try to illustrate down here when I drew the same picture with a kind of cut up. If you have a cone, you can cut it along the side and unfold it, and then you see that the around the cone point is really less than 360 degrees, so to speak. It has like a gap, which is this wedge on top of the top part of this diagram at the bottom right here, which is so all the gap is the part of the 360 degrees that don't exist at that point, so to speak. So although I have arranged the blue and the red line cutting each other at equal, slicing the neighborhood around them into equal parts like this, giving me these 4 equal pieces, nevertheless, those pieces are not the same as 4 equal pieces elsewhere. They're not 90 degrees, so to speak. They're less because there's less in total at that particular point. So if I repeated the process on another part of the cone, certainly I would get ordinary 90-degree angles, because in other parts of the cone it doesn't have this phenomena. It's just like an ordinary piece of paper, and it has 360 degrees like any. So, but the cone point is separate though, and that's where the whole process breaks down. So, in conclusion, then I have established that Euclid's postulate number 4, which at first sight looked almost childish and absurdly placed, like a strange mistake almost to include it. Nevertheless, I showed that Euclid knew exactly what he was doing. He had these kinds of scenarios in mind. He knew that he had a profound appreciation for these kinds of possible objections that might arise. So these have been some ways then of conveying the flavor of Euclid's elements with a view towards trying to highlight the how Euclid indeed has anticipated a lot of difficulties, and he has his work is very much more profound and perceptive than it might seem at first sight. So it is indeed justly considered a masterpiece of mathematics, and it is no wonder that subsequent history is largely modeled on his example.